Start. Okay. If you hear in the background, Mr. Lewis is sharpening his pencil, Sarah. So, anyway, start with, I believe we've got the elevator lab to discuss and go over.
We have robotics today?
Yes.
Okay. I wasn't sure.
Well, as I said in my email, though,
Because I wasn't sure because you said you had to go get Matthew, so.
I do, but check with Mr. Reader on how long he can be here. Also, you guys can work as long as you want.
Okay.
Yeah.
We call him Mr. Lana.
That
Mr.
works
R,
too.
yes.
But yes, I do have to go get Matthew after school also. But obviously, when I say after school, he's in Center Point at the daycare there, so obviously I keep from the daycare.
R.
Kristen didn't have to work till 3 today, so
Lord.
that's kind of nice. We take him to the
Thank you.
daycare. There's a daycare across the street from us. Alrighty, so from the elevator lab, you had to take and label the following as equal to, greater than, or less than the scale reading at rest. Okay, so then starting with that, from what you guys noticed for the elevator, so when you were at rest at the bottom, was it equal, greater than, or less than the scale reading at rest? Equal. Okay, what about when you're starting to go up?
Greater.
Greater, okay. Going up at constant speed. Equal. Slowing to stop at the top. It was less, okay. Stopped at the top. Starting to go down.
Less than.
Less. Going down at a constant speed.
Wow.
Equal. Slowing to stop.
Great high.
Greater. Okay.
Great tire.
Then you had to calculate the mass of the person on the scale in kilograms. So whatever your pound reading was. So pounds, I'm sure you took times 4.5 newtons per 1 pound. And then from there times 1 kilogram over 9.8 newtons, because there are 9.8 newtons per kilogram. So times 4.5 and then divided by 9.8. That would get you the respective masses in kilograms then. So now for the force analysis. Okay. Draw a quantitative force diagram for the passenger in each of the following situations during the elevator ride. Label the forces in newtons. To the right of each diagram, it said draw a velocity and acceleration vector that describes the motion of the person in the elevator. Calculate the net force and the acceleration of the person. Okay? There's my lovely little stick figure. Here's your elevator car. We'll just say something like there's a cable that's pulling them up, yada yada, you get the
It's actually the box attached to it.
idea. I must have missed something.
Oh no. Oh.
Depends which one you're talking about.
Yeah, if you're talking about them, I don't know what it is, but me and no, you missed absolutely nothing.
You can just watch it and figure
I'll watch a video later, figure it out.
Trust me.
I don't have the time to, so no worries. But hey, maybe Sarah will tell me later. Okay, so at rest on the bottom. So if we're at rest on the bottom, first of all, what's my force that's going to be pushing up?
Normal.
Normal.
Normal. Not normal,
Oh.
normal.
Rats.
Normal was a great cartoon
Yeah, I
cat
was
in
gonna say
Garfield.
that's off of Garfield, isn't it?
Yeah. Okay, and we're not going to, there's not anything going to the left or right. Okay. And of course, going down is
Gravity.
gravity. Should my arrow be equal for that first situation when we're at rest?
Probably.
They should
Yes.
be incongruent equality marks.
Incongruent.
No, they
equality.
should be
How's that,
in
Jaco?
congruent. Yes.
In
Not
space congruent.
in space congruent, not incongruent.
So they're equal to one another.
Yes.
Okay. So this is at rest, so obviously you wouldn't have a velocity vector, you wouldn't have an acceleration vector, you wouldn't have a net force, and your acceleration would be zero.
Approximately zero.
Yeah,
Roughly.
okay.
Rounding it up.
I mean, the movement of the Earth, it kind of sucks, but
It's kind of what keeps us here.
So then, velocity vector, acceleration vector, so it's starting to go up. Okay, so then if I'm starting to go up in my elevator, how would this change when I'm first starting to go up?
The upward force would be greater
Why would it be greater?
because you're moving up.
Yeah. Well, and at the same point too, what did your scale reading tell you?
It was up.
Yeah. So your scale reading went up. But after that initial thrust,
it leveled out.
in other words, for when we go to number 3,
And they're equal again.
then they'll be equal again. Okay, so then for number 2, we'll add on to this. So that would be your normal force. In other words, the black plus the red would be your normal force. It would be greater because you're accelerating upward. In fact, huh? That's right, yeah. Now, as far as the acceleration, we can actually determine that. And we can also determine the net force. If someone would like to give me what their, when they were first starting to go up, what their scale rating was, and then what their normal scale rating was. Josh?
Was that one?
Yeah.
Since you weigh more, wouldn't it be more gravity?
I'm sorry, what?
Since you would weigh more going up, wouldn't it be more gravity then?
Nope.
Because I want to see it.
That's the whole reason you're going up in the first place. It becomes greater than gravity. Can't accelerate upward unless you have unbalanced forces. Yeah.
Jacob's scale reading was at 190 at rest, and then when he started going up, it was 192.
192? Okay. Alright. So then in terms of newtons, and what was it, 4.5 pounds per newton?
It was 800.
So I guess there's a difference at, huh?
Do you want it in newtons? Or do
Well,
you-
yeah, because forces are in
Yeah,
newtons.
so it'd be 855 newtons and then 864 newtons.
855 compared to 864?
Yeah.
Okay, so it's a difference of 9 newtons then. Okay, so that means then in the upward direction, we have a net force of 9 newtons going upward then. Okay, so what I ultimately did then is I'm showing you the direction of the acceleration vector. The acceleration vector is obviously added on to the normal forcing. So in other words, I'm saying that this is all normal force. Obviously, that's the addition of that. You'd be accelerating upward. And the net force would be 9 newtons. So then from that, let's see. What is Jacob's mass in kilograms then?
Just at rest?
Well, I'm just talking in general, because 190 would be his weight at rest, so that way we could get an accurate mass.
85.5.
What? I had 87.
That's
Let's
what
try
I
190 times 4.5 divided by 9.8. Yeah, 87.2.
I just divided
Yeah,
by
it's divided
10.
by 10.
Okay.
That was me.
So let's just call it, to be even, let's call it 87. Okay. So Jacob's mass is 87 kilograms. So 9 newtons equals 87 kilograms times A, my acceleration. So 9 divided by 87 gives me an acceleration of 0.10 meters per second squared. So that means we have an acceleration of 0.10 meters per second squared.
That's really, really not fast.
Well, and as you felt, obviously, you just kind of had a quick initial thrust and then it stopped. So obviously, I mean, if the scale didn't go up that much, does that make sense then?
Yeah.
Okay. Otherwise, if it would have been a greater acceleration, what would have happened to the scale?
Would have went crazy.
Yeah, would have went even more crazy. Would have went a lot higher. Okay, now, situation 3, going up at a constant speed. Actually, I didn't do the velocity vector for the second one, did I?
No.
Okay. So what would my velocity vector look like for that one? Okay? It would go up. Now, as I'm showing, let's say if I show like 3 arrows, would I show them all the same? Or would I show them like getting bigger, getting smaller?
Bigger.
Getting bigger, yeah. So for the velocity vector, you'd want to show something like, just to show that it is increasing for the velocity vector.
Yeah.
Now for the acceleration vector, obviously,
Constant.
it could just be a red arrow.
One.
You know, that are constant, they're the same size. For going up at a constant speed, number 3, are my velocity vectors same size or different size? Okay? Acceleration vector,
There is
there is none.
It doesn't accelerate.
Net force,
none.
There.
huh?
No.
0. Yeah, there is no net force. So in other words, my arrows are equal. So if I'm going at a constant velocity, there is no net force either direction. A net force ensues that you are either speeding up or you're slowing down. You're going either, you're accelerating or, so in other words, you're either accelerating or you're not in order for there to be a net force. So if you're accelerating, you got a net force. If you're not accelerating, there is no net force. Okay, 4 then. Then of course the acceleration at the end for 3 is 0. 4, slowing to stop at the top.
It'd be more gravity than there would be for
Correct, yeah.
normal. Sorry.
So then, you, what you basically do is gravity never changes. So then, if gravity doesn't change, what has to change?
Your force of normals.
Yep, the normal force.
Star Wars there.
Okay?
The force.
So then the normal force would decrease.
Difference in the force. Billions of officers fighting in pain.
So your normal force would now be less than gravity, causing you to slow down. Let's throw a little Newton's third law question at you.
I don't remember what it is.
Okay. Actually, let's
There's
let's-
the three.
Well, I always see the first one and the third one mixed up.
Newton's third, okay,
Is that
equal and opposite.
Yeah. Okay.
Equal and opposite, yeah. Okay.
We can move on and do that now if you like.
Anyway, so, going on, so then slowing to a stop at the top, so obviously the normal force is, less. Which, by the way, what I'm saying by that is that, I had it on the tip of my tongue there, honestly.
It's slowing down.
Yeah, it is slowing down. I was
Yeah.
just trying to think in terms of
Math.
equal and opposite, but anyway. I think I'm thinking about the like the force of the car on the cable, and then the force of the cable on the car would be equal and opposite. But anyway, I won't get too much into that. Okay, so slowing down to a stop at the top, what would my velocity vector look like as we're slowing down then, but we're still going up?
Starting bigger and then getting smaller going down.
Right, so bigger, smaller, smaller. As we are going up, we're just, obviously, we're lessening in terms of our
We're just
velocity.
not going up fast.
Yeah. So we're slowing down. Now, what direction would my acceleration be in then? Downward. Yep. Because since gravity is downward, the acceleration would be in that direction. So my acceleration would be downward, even arrows. Okay. And then to calculate what that net force and acceleration would be, okay, what was Jacob's weight then as you were slowing down to come to the top?
180
180.
in pounds, yeah.
Okay, so 180 pounds.
110 or 810
Here's the
newtons.
donuts that I had.
Okay.
That was the donuts that I had that one.
So that'd be 10,
Although, I was
10
wearing a coat
times
And a sweatshirt.
4.5
and boots.
divided by
So
10.
it probably didn't help the fact out. So much stupid gone.
Okay, so it'd be a difference of 4.5 newtons, what I have.
4.5.
Or, what am I doing? I'm sorry.
Yeah.
45, right?
Be 45 newtons. Oh my. Okay,
No.
so 45 newtons equals 87 kilos times acceleration.
Is that expensive?
So 45 divided by 87. He'd have an acceleration then, as we're slowing down, of about 0.52 meters per second squared. And actually, that would be in the negative, because we're talking, we'll refer to it as up being positive, down being negative.
I decelerated faster than I accelerated going
See.
up.
But he's not going down.
Huh?
He's not going down.
He's not, I know. But the acceleration is in the downward direction.
Oh, okay.
Because again, the upward force is less than outward. Yeah.
Technically, I'm always falling,
I'm
so...
just exhausted.
Then again, what is
If
falling?
it's not you.
No, I know. It's okay. It's okay.
Dun, dun, dun.
Trust me, I've been dealing with emails from tournaments all days, and I get an email from your mother about concession stand, and then
Oh, yeah, just over the colder horses.
No. I responded as soon as I could.
I don't have any
Got it
horses.
taken care of.
I just find it amusing people say that to me. Like, hold your horses. I'm like, well, I
Well,
have some. I wouldn't hold
She
them.
was right to me, they needed to know what they
That's why I wouldn't
needed to
even
know.
hold them.
Actually, Speedy Shop needed to know, so that's a good thing. Okay. So that was slowing down to stop at the top, okay? Stopped at the top, that should be a nice, easy, squeezy, lemon peasy one. Velocity vector. Stopped at the top.
None.
Got
0.
Wasn't going anywhere.
Acceleration vector.
nothing.
Net force.
Nothing.
0.
Acceleration.
0.
Nothing. Yep. Zeros.
Accelerating. Or we're always having velocity.
Okay, starting to go down. Down. Jacob's going down.
The ring of fire. Ring of fire.
Okay, velocity vector.
Starts smaller, gets bigger going down.
Yep, starts smaller, gets bigger and bigger. How about this for you, Jacob? I fell into a burning ring of fire. Oh, down, and the flames got higher, and it burns. The ring of fire, the ring of fire.
Hotel
Yes.
California.
Yes.
Good, bad, awful.
I'm
I'll give it a
ranting
7.
about why I don't like that song.
It was decent, that was pretty good.
Huh? Thanks a lot.
But no, I thought
I'd make it to all state.
You just don't like my singing, period. Even though I actually sing it according to how the song would be. So, thanks a lot, Adrian.
I didn't say anything, it was just funny.
Okay. I was gonna say, I won't be mean then.
This bottle has
I
approximately
know, we're on the
100%
fucking
vitamin C.
No,
Okay, that wasn't
It's a
where I
shame
was
we
going
don't
with
eat
it, okay? I was not going with that.
It's okay.
I was not going with that.
It's alright.
No, she doesn't. She doesn't
It's a
know.
shame they put that
So she
stuff
couldn't
in
hate
there.
you, she didn't know.
Just use help. Dump it out.
Hey, hey, hey.
What was that for? The bottle said 100%.
Okay,
vitamin
so
C.
we've got
Tastes like apples.
We've got the velocity vector obviously continuing to increase as we're going down. What would our acceleration vector look like?
Constant going up.
Nope.
Cuts
Constant
down.
down. Because, same situation here in terms of our force diagram, gravity is going to be greater than the normal force. Okay? So, gravity is going to be greater than the normal force, allowing us to come back down. Okay? So that would be for the vectors. Now, when you were first starting to go down, what was your weight according to the scale? Or what was Jacob's weight according to the scale? Huh?
Going up.
I'm just asking what the reading was.
Starting to go down,
Yep.
it was 180.
It's 180. Okay, so it was the same
Yeah.
180 again? Okay, perfect.
Kids is
So
going down.
then we still have that same acceleration. So it tells us the elevator does the same thing then as it's close to the top floor. It does the same kind of acceleration for slowing down to the top and then going down from the top. Okay. Alright. Then, of course, going down at a constant speed, we'll have 0 for the velocity vector. We won't have any acceleration vectors. Our velocity vectors will be constant.
Constantinople.
Our force diagram will have equal arrows going up and down, so normal and gravity will be equal. Net force 0, acceleration 0. Then lastly, slowing to a stop at the bottom. So, in terms of the force diagram, if we're slowing down, coming to a stop, how's normal going to compare to gravity?
Higher.
Higher. Okay. So normal is going to be higher because we're going to want to resist going down anymore. So we've got to accelerate then in what direction?
Positively.
Upward, yep. Because the net force is going to be in the upward direction. So acceleration will be constant going upward. Velocity will be larger in the beginning, getting smaller.
Slow down.
Yep, because we're slowing down. So those are the vectors. Was your reading something like 192 again as you're slowing down, coming to the bottom? Or was it a bit
I
different?
think it was 192. It might have been a little higher because it was
Okay.
a bigger jolt when we hit the bottom, but
So we'll go with 192 again. Okay, and the acceleration being that, a positive 10. Huh?
So those donuts really didn't help that
You don't know.
one. Actually.
Unless you're chancing, then you're weighing yourself a bunch, right?
Oh, yeah.
Huh?
I have donuts.
You can have donuts now?
Not right now.
Oh, okay. Okay. You guys have meat tonight, don't you? Where? Here?
Hope you lose.
Well, yes.
Someone
I
who's
hope
much,
you do bad.
so someone who's much better than you, so you can learn from the experience.
Okay.
there's a big
Odd
Lisbon
compliment of the
guy.
day.
He looks big, but he's not good.
This really tastes good except for like the raspberry.
Alright, so that takes care of all that. Do we want to do like a recap of this quick? Or are there any questions on this?
Sarah, do you have
I'm sure she'll have questions for us tomorrow.
Say nothing if you're okay with us moving on. Good, good. Continue. Did we do
Okay.
number 9?
Now, how about this? Actually, while we're at it, I'll get you homework here in a moment, but why don't we at least get kind of the table set for tomorrow, so that way we can start a lab. It will not be a lab report, so no worries about that.
Phew! It's not the other one.
I will give you guys homework credit for the elevator lab. I may also give you a little bit of like participation credit for the activities part too.
I don't know. I did nothing except just stand there.
Okay, you have to make observations, and you have some work to go with that, so you do feel that that's worth something. Okay?
Are we picking groups for this lab?
You want me to draw, or do you want
I
to
don't
pick your
wanna be in
groups?
her group. Yeah.
Good, I didn't want to be in your
I
group
don't
anyway.
like you.
I don't like you either.
You're weird.
Coming from the person who just leaves this much apple juice.
It's not even apple juice. It's apple cran raspberry. Actually, it's cranberry apple raspberry.
Apple cream raspberry sounds better.
Better? It's not better, guys. That's totally better.
How about this? As we all know, as I'm moving this across the table, what forces are acting on it?
Mmm.
Friction.
Normal. Oh.
Friction, normal, gravity.
Pulling.
Yep, and my pulling force. Okay, so friction, normal, gravity, and my pulling force. Okay, so what might be affecting the amount of friction that is being caused between my object and the surface in which it's in touch with?
Weight.
Fast you pull it.
Okay, so ideas are weight. In other words, mass. Okay. How fast, so the velocity at which I'm pulling it. Okay. Other ideas.
Friction on the table.
Okay, so
If it's a frictionless surface,
how about the type of
there
surface?
you go. Dragging across gravel would be different than across ice.
Okay. Type of surface, whether it be, are you talking the bottom surface, or also, I guess you could,
Both.
yeah. So you could also include not only the type of surface for like what's on the bottom, but you could also include like what type of object you have.
Yes, using sandpaper. It's different.
Then making it go on oil.
By the way, I do have sandpaper around for that purpose too. Okay?
Question.
Yes.
No.
Could something theoretically have 0 weight?
Everything.
It's
In
just
order
like, that's
In
preposterous.
order for it to be classified as an object, what does any object have to have? It has
mass.
to have mass. Yeah,
Well,
any
that's
object is
like-
made of atoms, so
I-
there's really no thing as having, there's no such thing as having no mass, because it could be really infinitesimally small, but it would still have a little bit of mass to it because it's still made of atoms.
So
It's not like absolute zero.
Right. So if it's an object, it at least has a few atoms to it.
could it have 0 weight? Is that possible? Be the same
Now
weight?
you're getting into another question, because weight. What are the components of weight that we discussed?
Gravity and mass.
Yeah, so you could theoretically have 0 weight, 0 gravity,
That's right.
okay? But you can't have 0 mass.
So we need to find a place that has 0 gravity without going in space because that's
So,
really difficult.
What I'd like you to do in this quick lab, I guess you could say, obviously we'll start it first thing tomorrow. You'll need, obviously, force. You'll want to use those dual range force probes, those force sensors. That looks like farce. There we go. So you'll want to use force sensors. Then obviously you can find objects of different kinds to work with.
My foot.
Use your imagination. My room is
My
your
imagination
playhouse.
is a dinosaur.
Honestly, I've got masses, I've got
No.
sandpaper, I've got wood blocks. Really, anything that you can think of that you could hook up to that force sensor, because I also have string that you could like tie knots to objects and then drag it along. So, honestly, use your imagination.
Don't let Jacob use his imagination.
My imagination is very dangerous.
Okay, so realistically, we've got 3 different tests that you can do. You can do force versus mass or weight, whatever. Actually, I guess you'd call it weight or weight, whichever. Velocity, and then your surface type. Or at the same time too, you suppose maybe, would this have a difference compared to this?
Yes.
Why?
Well, theoretically, we can't prove it right now, but I'd assume this has bigger surface area.
Okay, so we can also take a look at surface area.
Yeah.
So the surface area of an object. Maybe if you want to try the same object, but try a bigger versus a smaller piece of an object. I do have wood blocks that you can do that with. You can also obviously try surface types. Okay? So we'll start that first thing tomorrow. Homework tonight. You're going to have worksheet 1. I'll happily run that off. It is dealing with the lab. I'll also send it out electronically via Google Drive. It's basically, it's everything from the elevator lab. Okay? Let me shut the camera off and I'll go around
No.
off, also send them on
You
my
can't
Google
shut
Drive.
it off.
One moment.
It's my friend.
And that concludes our broadcast day.